In this chapter of our forecasting course, we're going to talk about a brief history of forecasting competitions. So starting obviously with the M competitions, I'm following here mostly a paper by Rob Heinkman from 2020. And so let's start with this paper from Makridakis and Thibon, 1979, in the Journal of the Royal Statistical Society, Series A. And in this paper, they benchmarked a bunch of time series methods against each other on 111 time series. And what they found was that simple methods such as seasonal naive or simple exponential smoothing worked often better than a REMA, which at that time was considered a complex method. And yeah, it's interesting that back in 1979, this was a kind of a new controversial idea that you actually test your models on data and look how well it works. And so in these papers, it's often customary to publish a discussion alongside with the paper. And so in this discussion, you can read things like, I find it hard to believe that Box-Jenkins, which are their REMA models, if properly applied, can actually be worse than so many of the simple methods. For example, that's a comment by Chris Chetfield, a leading statistician at that time. And there are many other comments along this line. So back then we had a strong belief that there is a true underlying data model that can be discovered, and that this underlying model will necessarily give the best forecasts. So consequently, the discussants questioned the ability of Makridakis and Thibon to use methods like REMA properly. And they didn't agree with defining that forecast combination works well, which is something we would nowadays call ensembling. So, based on that, Makridakis put together this first M competition named after him, M1 competition run in 1982, so over 40 years ago. And yeah, to answer the criticism, Makridakis organized this competition where contestants could submit forecasts, right? So the idea was, well, if you tell me I don't know how to run these methods, well, you run them and you submit me the forecasts and we see how well they work. It was 1,001 time series, and the results largely confirmed the earlier results. The best method was a seasonal naive combined with simple exponential smoothing. Forecast combination worked well. And the consequence of this was that forecasters focused mostly on out-of-sample accuracy rather than model properties, and forecasting emerged as an independent field from time series analysis. Well, then there was an M2 competition that was a bit more, it was a bit different, and it hadn't had such a big impact. So the next important one was the M3 in 1998. The results are published in this paper, Makridakis and Thibon 2000. It had as a central conclusion again that complex methods do not necessarily outperform simple methods. And again, ETS and the REMA were the complex methods, and simple methods were models like a random walk with drift, which is basically just, like a random walk, and then you put a constant to it, a drift term. So the only neural network that participated was quite bad, and it was won by a method called the theta method, which was later shown to be an average of a linear regression and a simple exponential smoothing, again with drift. The M3 dataset was afterwards the benchmark dataset in forecasting for almost 20 years, and there was a lot of focus on this dataset, probably too much focus. Like for 20 years, people were kind of just very trying very hard to perform well on this data set. And obviously a bit of overfitting certainly has happened on this data set. Yeah, so that explained why, and now the controversy of machine learning versus statistical methods. So yeah, there is this controversy in the forecasting field whether machine learning or statistical methods work better for forecasting. This discussion went on for a long time because forecasters, they knew that simple methods work best. They had not only won the M3, afterwards they won the NN3, NN5 competition, which were competitions particularly designed for machine learning methods for neural networks. And on the other hand, you had the machine learners that kind of knew that neural networks work best because, well, it's a neural network, you know, it always works best. It's a universal approximator. It can approximate everything and anything. So you will find thousands of papers in neural network journals and others that always go more or less like, we have this great new method and we use it for stock market forecasting and we forecast these 5 stocks. And I'm always like, well, why these 5 and not any of the hundreds of others that you can readily download from Yahoo Finance, for example. So it's always cherry-picked data sets, no proper benchmarking, and yeah, not very rigorous. So then, in 2018, Makridakis wrote another paper, Statistical and Machine Learning Forecasting Methods, Concerns and Way Forward, where Makridakis and the co-authors benchmarked machine learning methods against statistical benchmarks. Not surprisingly, again, the machine learning methods lost, didn't perform well. And the interesting thing is that this paper is published in PLOS One because it got rejected at 2 to 3 neural network outlets beforehand. And now the reasons for rejection were that there are many machine learning methods that have proven to overcome the results provided. Though the editors and reviewers didn't name any in particular, it was just kind of, you know, we already know machine learning works, so you must have done something wrong. So history in that sense repeated a bit, and Makridakis was probably upset about that and did what he then knows what to do, which is organize a competition, which was then the M4 competition, so that the machine learners, well, they could submit their own forecasts and show that their methods work well in a competition setup. Yeah. So I hope that this history explains to you why the forecasting field got so hung up on this controversy. It is still a bit surprising that there were these hostilities, but these kind of, you know, different approaches, because forecasting emerged from statistics just in the very same way that machine learning emerged from statistics, which is focus on out-of-sample accuracy in favor of model properties. And yeah, so consequently, some things were discovered in parallel in both fields. Forecast combination that was discussed in this seminal paper from Bates and Granger in 1969. And then ensembling came up in machine learning sometime in the 90s. Simple methods in forecasting versus regularization in machine learning. Right? So forecasting and machine learning are 2 fields that I think they've always been, or you know, they are able to really learn from each other. And I think still today that is true in the forecasting field. Obviously, machine learning, it moves at a way higher speed. But yeah, I still think if you work in this area of forecasting, then you need to know both about forecasting and about machine learning. And that's obviously what this training course is about. Yeah, so then we got to the M4 competition. That was in 2018. That was then 100,000 time series across many different domains. We had now also a bit more high frequent data, hourly, daily, weekly, and then again monthly, quarterly, yearly. Also, prediction intervals were required. The results are published in this 2018 paper. And I guess it's fair to say that most forecasters expected that a combination approach of statistical methods would win. But these methods actually got 2nd and 3rd place. And the winner was a big surprise, which was this ESRNN method that it's called, which is a hybrid between an RNN and ETS by Slavek Smul, 2020. And yeah, it was a big surprise to many people that machine learning now could win such a competition. It was not so much a surprise for me, because actually 2 years earlier there was this CIF2016 competition. And I actually got beaten in that competition already by Slavek 2 years earlier. It's an interesting competition because the data set is so small and so kind of made for statistical methods, you would think. So it's only 72 monthly time series that have a length of 22 to 108 data points each. I participated with just plain ETS and with another algorithm I had developed earlier with Rob Heinemann, which is backed ETS, which is kind of just a bootstrap backed version of ETS. Backed ETS won several subcategories. It was also winning on median SMAP. But actually on the competition metric, which was the mean SMAP, backed ETS got 9th, plain ETS got 3rd. Yeah, and first and second place were actually LSTMs from Slavek Smil. And they were globally trained across the series. So one LSTM for all series. So what you get from this is that ETS was still very competitive, 3rd in the competition, just auto ETS. Slavek Smul was able to outperform that with an LSTM, which is quite remarkable, that if you have 72 monthly time series, for me that would not be the main use case where I would say let's use a recurrent neural network, but he managed to do that. And yeah, the way he did that, that's even the most interesting part. He did it in a globally trained way across the series. Okay, so that concludes our first kind of big part of the training course. And the next part is obviously then starting with the global models, so that we can see how the global models can now work on forecasting and how machine learning can now actually work competitively on these forecasting methods. Thank you. Here I put your link to my webpage, cbergmeyer.com, and my email address. Thank you very much.